Okay. So I just write down once again the material that we are supposed to do today. 2.3 and 2.4, those are the sections from the book. So this is Jordan decomposition. And there are other things as well. And this one, so G every linear algebraic group can be realized as every affine algebraic group can be realized as a closed subset of closed subgroup, Zariski closed subgroup of some GLN, and therefore it's a linear algebraic group. Okay, so while that is the main statement, there are I mean, it's not enough that you just know the statement, right? I hope that must be amply clear by now, because the method of proof is just as important and part of the course. So let's just recall quickly what we were doing. So G was G was take G to be a linear algebraic group, X to be a G variety, affine, and then what we said was, given F or V, a subspace finite dimensional of Kx, Kx is the ring of functions on X, right? X is an affine variety in particular. Therefore, this is the ring of functions on X, ring of polynomial functions on X. And so, given all this, there exists W G invariant finite dimensional such that V is contained in W. Right, and so W space. So this is a K vector space, K subspace. K subspace of Kx, such that this happens. Okay. Now let's the proof is also important. So I did this towards the end of last class. So let's go through the proof once again. So proof, very quickly, is may assume V equals F. V is just the span of, or let's even write Kf. Because if we did it for just one-dimensional space, then by choosing V can be written as a sum of one-dimensional spaces. Obviously, anything can be written as a sum of one-dimensional spaces, and V is finite dimensional, so it can be written as a finite sum of one-dimensional spaces. And for each one of those finitely many one-dimensional spaces, if you choose a finite dimensional W, the sum of all those finitely many W would also be finite dimensional and would be G invariant, and you would be done. Okay, so you may assume this. And what we did was we took this F, right, and then we took this delta of F. Let me write. The book writes A star of F, but let me write delta of F. So delta, what is delta of F? So G cross X to X, there is a map. that's which makes X into a variety, G space. Now, everything being affine, that is no more, no less than there being a K algebra homomorphism the other way. Okay, this is what we have called delta now. Right, delta is a multiplication map, if you wish, or co-action map. So I take F here and write it as a and something. So all tensor products are over K for the base field. Okay. So what does this mean? Elements here are something here, tensor something here, sum of finitely many. Okay, it's finite sums of something here, tensor something here. So I can write this as Fi tensor Hi, or I equals 1 to n. So this is finite. Okay, so what does this mean? So let's write, the way we wrote it was, we wrote G of F, right? Let's do G of F of X. So I am interested in all, so what is the logic or what is the motivation? I am looking for all, Niltanama. Okay. I'm looking for all, I want a W which is G invariant and contains F. Therefore, it must in particular contain all those. So I try to evaluate, see how they behave. So I take an X, look at a G of F and try to do this. Now this, by the definition of this, is right. Okay. Now let us understand this once again. So this is G inverse X going to G inverse X. This is the action map, right? And what does delta mean? Delta is the pullback under this map. That means if I take delta F, so what it means is if I act F on something, on an image of something here, say G inverse X, it is the same thing as I apply delta to F and act it on G inverse X, G inverse comma X. Right. Now delta of F, we have assumed it's of this form. This just, we have just written it out in some notation. Now, so I should act this on this. Now, a general fact, if I have X cross, if X is an affine variety and Y is an affine variety, its ring of functions is Kx tensor Ky. So, for if I take something F tensor G here or F tensor H, how is this a function on this? F acting on X comma Y is simply Fx times Hy. Okay, that's how. Okay. Okay. So now, so therefore, this delta, so it is a sum of Fi tensor Hi acting on this. So it is a sum of what this acts on that, and so this will be equal to sum Fi G inverse Hi X. Right. So that's what we write. So this is equal to Fi G inverse Hi x, and this sum is the same. Okay. Now, x being generic, you can write what you get is that g of f is equal to f inverse hi. Did I get the? Okay, I should have. Okay, allow me please to just switch this. Not that it matters, but it is better psychologically. I should have chosen f's for functions on x, h some other symbol for functions on g. F is a function on x, so I should choose the same kind of thing here. So this should have been hx. This should have been hx. Sorry. This is okay. This is okay. This should have been h here and f here. I hope I'm doing this. Please watch me. Is this okay? And the point is that these are, if you think of a given g, these are just scalars, and therefore this belongs to the span of f1, fn. Let's say this was I equals 1 through n. So, I repeat, the argument is not that this is G invariant, that we don't know. But the point is that every translate of f is contained in a finite dimensional space, this particular finite dimensional space, right? So, you obtained a space which is finite dimensional and contains all translates of f, and therefore, you see that GF f G in G, right? The span of this, when we write this, it means various things at in various contexts, but here it should mean the k span of those elements inside k of x, right? This is inside k of x, the k span of these elements. Okay, this is obviously G invariant. No problem, we could have done that even at the beginning. The problem is what you don't know about it a priori is that it is finite dimensional. But then what we have observed is that this is contained in f1, f2, fn. Therefore, it is finite dimensional. Okay, so implies all right. Is this clear? Okay. Yesterday at the end of class, some people were asking how explicit is this delta. It's actually quite explicit. For example, let's do the case when, let's do G cross G going to G, right, mu. Let's take GLN cross GLN going to GLN. So you have KGLN going to KGLN tensor KGLN. Right, this is the usual matrix multiplication. How do things look here, right? So it is enough. So this is what is this? This is I adjoin n square variables and then put a determinant inverse. Okay, so that is this ring. Okay, now it is generated by meaning I. Okay, so let's look at what happens to xij, where I and j are between 1 and n, in the obvious notation. What do you think should happen to it? if you think through it, what should it do? I take two matrices, and what should I write here? It is a sum of something from here, tensor something from here. Okay. Now this should be such that when I take two matrices and then evaluate this thing on that, meaning sum over, the first one Fi Hi, if I write Hi Fi, then Hi on the first one, Fi on the second one, and sum, that should be the same as I multiply them and take ijth coordinate. Okay. Now what is that? It's just the following. You think about, I take two matrices, multiply, I get something, and take ijth coordinate. What is that? Ijth coordinate of the, it looks complicated, but you can think more intuitively like this. Take two matrices, multiply, what is the ijth coordinate? Well, the ijth coordinate is the ith row times the jth column. So I have to write, so this as we all know so this is, you should think of this as the coordinate on the product. So if you should think as if it is AB of ij. If I write that, then that's the same as aik b kj, right? Okay. Now so I mean, that's how it works. So what you would write here correctly is I sigma k is equal to 1 to n I k tensor x k j, right? So it is just the usual multiplication written out, as pullback of functions. That's all it is. Okay. So there is nothing mysterious about this or that. And it would be a good idea if you worked out, for example, in certain cases, what exactly, for every group that we encounter, it might be a good idea for you to work out how to write the inverse, how to write the co-multiplication and all these maps. Okay, now let's so the second statement was that V is stable under G if and only if delta V is contained in Kg tensor V. Right, delta V you can write as a sum of things, right? If you choose a so you could do this, you could think of this as follows. I choose a basis for kx by first choosing a basis for V and then extending it. Okay. Then so what it means is I take a basis element of V, say F1. So V is a finite dimensional space. So it has a basis, let's say F1, F2, Fn. Right. Now I take F1, look at it, write it on the other side. Now a fact about tensor products is over a field, if this has a basis and this has a basis, then the dimension of this is the product of those two dimensions, and the bases are for every element here and for every element here, this tensor that is a basis, right. So, delta of Fi will be an element here, and therefore, I should be able to write it as a linear combination of basis elements. So, I choose a basis, and here I have chosen a basis for kx. I mean, a priori I do not know whether it is V. So what I am doing is, so I am not sure if I will prove this entirely, but at least I will the crucial way to think is probably is to choose a basis for kx by extending a basis for V. That is what makes the proof go smoothly. So let F1 Fn be a basis for V, or V extend this to kx. So let it be F1 Fn and then Fn plus 1, etc. just for, okay. And then delta of F1 you can write as see, there is a uniquely, this expression is now unique, is F1 tensor H1 plus F2 tensor H2 plus dot dot dot. In fact, going beyond, so this goes beyond n a priori, right. So do you see the following, that this is a this expression is unique Fi are in Kg. Sorry, Hi are in Kg. Right. So how do you, one way to think about this, I am claiming this expression is unique. These Hi's are in Kg. Why? For example, one way to think is just take this delta F1, right? So choose some basis for Kg and then write out everything explicitly, right? And collect, so all the ones with F1 on the second coordinate, you collect all the sum, you can sum all the Kg's there, elements of Kg, and that will be H1. Okay, all sums are finite. Although we are writing infinitely many, this is a finite sum. Okay, almost all of which is 0. Okay. Now the point is, the claim is that V is stable if and only if. So this is what the claim is. G stable if and only if the others are 0. That is Hn plus 1 that's what it means. Okay, so maybe I won't do this proof in class. It's a good exercise for you to try. Okay, and if you have difficulty, of course we'll discuss. Okay. Okay, let's move on. Okay, now let's prove that theorem, the embedding theorem. Okay. Okay. So I have to find a GLN, right? Okay. So there is a part here which is also important, and that is, so if in such a case, if so, that is if these equivalent conditions hold, then V becomes a rational representation. V is a rational representation of G. Okay, in all this, what is unsaid is the action of G on Kx that we are tacitly taking is that left one induced by left multiplication. That is, G of f acting on x is f of G inverse x. Right. So V is, when we say V is stable under G, it's a subspace which is stable for this action. Okay. The claim is that this is a rational representation. So not only is it finite dimensional and stable, the map that you get from, so you will get a map from G to GLV, right? That map is a polynomial map. I mean, more precisely, morphism of varieties. Okay, that map is a morphism of varieties. Now again, I'll leave that for to you to check, and if there are difficulties, please do ask. Okay. Okay. So now let's think about what we want to do. So what do I want to find given a linear algebra, given an affine algebraic group? I want to find, see, if I just wanted this, there is no problem, right? I could just map everything to 1, right? Sending everything to GL1, just the element 1, for example, is a you get a map. What the important thing is that it embeds, right? Okay. So observe that whenever what does it mean to have a rational representation? It means to have a algebraic group morphism from G to some GLN. So whenever, and it is equivalent. So just as in contexts that you are familiar with, say, what does it mean to be for a linear representation of a group? Of course, you will define that there is an action as if it's as a set of G on V, and it is linear. You can say it like that, or you can say there is a group homomorphism from G to GLV. Here, of course, being in the category of algebraic varieties, we will say G to GLN is a group homomorphism, but in addition, it's a morphism of varieties. Okay. So it's no more, no less than. So I have to find, what do I have to look for? I have to look for a representation, right? Where do I find a representation? Well, here I have found some. That proof gives me some. I choose some f, right? And then I have shown that I choose a function, any function on the group. Yeah, first I have to find an x. For the x, I take the group itself, right? So I take the group itself, and then I look at kg. I look at a function there, any function, and it is contained in a finite dimensional G stable space, right? So I can choose that, okay? Or just look at this. This is one of them, okay? Okay. Now, so you have representations, right? But what do I want? I want this to be an injection. I want this to be a faithful map, faithful representation, right, in the sense that you understand from finite group theory, right. You want this to be a faithful representation. So somehow I have to, it has to be big enough. Okay, and the idea is the following. So you use this. So I repeat, I said this last time, I will say this again. If you are familiar with Lie algebras, so when you are looking at a complex semi-simple Lie algebra and you want to find a representation, the most natural thing to look for when you want to prove something generally is the adjoint representation. So here, sort of the analog is looking at Kg itself. It's an infinite dimensional space, but as we have seen, it is locally finite in the sense that every element, or more generally any finite dimension, given any finite dimensional space, it's contained in a G stable finite dimensional space. So it is a union of finite dimensional spaces. Okay. So although it is infinite dimensional per se, but it is it's nevertheless very good because it's locally finite. Okay. So I repeat. So I take this God-given representation. I know that there are many finite dimensional ones. In fact, if I take any finite dimensional subspace of it, it is contained in a finite dimensional. Now, question. I want a big enough finite dimensional space here, big enough but still finite dimensional space here, such that the resulting action of G on this vector space V becomes faithful. Okay, what is the natural thing to take? Well, what do I know about my variety? It's K is an affine variety. Kg is a affine algebra, which means in particular that it is finitely generated. So it has finitely many generators. So hopefully, if I just take all the generators or take some set of generators, put them in, and of course I am not going to take the algebra generated by them, that would be the whole ring, that would be too big. I just put them into my, take a finite dimensional space containing all of them. And G stable space, finite dimensional, containing all of them. Hopefully that will work, right? Because somehow all the information about the group is contained in Kg, and that is contained, at least intuitively, in these generators. So it should work, right? So you try that and it works. Okay. Is it clear? Okay. So I will be very sketchy with my proof. So point is to find, or the point is to find a faithful rational representation. It's no more, no less, right? If I find a rational representation, that means there is a map from G to GLN. If it is faithful, that's an injection. There is also the bit about closed, but that's already okay, because any homomorphism, the image of any homomorphism of algebraic groups is closed, of linear algebraic groups is closed. So that is for free. Okay. So this is all there is. This is all you have to do. Okay. So claim let V be a finite dimensional G stable or G invariant or G stable subspace of Kg with the left action unless otherwise stated, containing all containing a set of algebra generators or k algebra generators of Kg. The whole point of the earlier thing is that it exists, such a thing. So there are finitely many, you can choose a finite set. I have just said containing a set of, but you can choose this set to be finite and then take the V to be take the K span of those. That's a finite dimensional space, and then we know from the earlier thing that there is a finite dimensional G invariant space which contains that, and so we are, the whole point, as I said, is that it exists. So now all we have to do is that this is faithful, right? Okay, let's see. Now that's the only thing to really check. So faithfulness. Suppose I will be very I'll write it like this. Suppose G is an element of the group. Suppose it goes to 1. I have to show G itself is equal to 1. Okay. What does it mean? It means G of Fi is equal to Fi. For all generators Fi of Kg. Because this is how it acts, but it's going to 1, which means this is just Fi. Now G is an algebra homomorphism. G acts as algebra automorphisms. See, every element of G, when I translate it on G, say, so G is a variety morphism, right? So if I multiply, so think of, given an element of G and given the group G, I look at the left multiplication action on G. I take an x and send it to Gx, right? X going to Gx is a variety morphism because it's the restriction of the multiplication map to G. So it's a variety morphism. Therefore, the left multiplication by G on functions is an algebra morphism. Okay, so therefore, if it fixes generators, it fixes the whole algebra. Okay, so what it implies is, this implies, since G acts by algebra automorphisms. What do I get? I get that G F is equal to F for all F in Kg. Right? So let's write it out. G of F of x is equal to F of x, or even put 1 for all F. What is G of F of 1? By definition, it is F of G inverse of 1. Implies, can everybody see this, or should I go there? Should I move there? No? Okay. This means F of G inverse is equal to F of 1 for all F. Okay. So I have 2 points on my variety, 1 and G inverse, where all functions are the same. Okay? But that is not possible because I am on an affine variety. There are functions. So, it is see, for example, if you were on a projective so-called, okay, we have not talked about this, but it is possible that if there are varieties, suppose you have something called projective space, for example, global functions are only constants. So, it is not possible to find functions. See, on a general variety, you cannot say that there are functions separate points, but the point of an affine variety is that it has enough functions. Okay, so given two elements, I can find something that is 0 here and non-zero here. Okay, that's like saying so what amounts to, that amounts to another way of thinking about it, and in fact we will, this is how finally affine varieties are defined. I mean, of course we have defined affine varieties already, but the way, if you look back at chapter 1, the way it proceeds after this naive definition that we have given of affine varieties, the next step is to give a more abstract definition of affine varieties, and that is done as follows. So let me mention that here. So we know that affine varieties are in the category of affine varieties and morphisms, is the opposite of the category of affine K algebras and K algebra morphisms. Okay, so so let us think for a minute on, suppose I give you an algebra. How do I find the corresponding variety? Well, what you do is it is a finitely generated algebra, that is part of the affine definition. Therefore, you will choose a polynomial algebra in finitely many variables over the field K and map it onto this algebra. Okay, so and that n will determine the affine space in which you are taking. You want to get your loci, you are going to take equations and look at points sitting inside that affine space. The problem with this definition, if you want to do this is fine, it's intuitive, it works fine, but except when you want to start prove things with it, then you might choose one, I might choose another, etc. There is always this after you've passed the initial stages, when you're convinced that this is the right definition, but now you want to do it in a way that it's more abstract perhaps and less obvious, but nevertheless convenient for proofs. Okay, so what you can do is the following. You can think of, so use the Nullstellensatz. Okay, so I'll put this word on the board, so that if you don't already know, you should. There are various versions of the Nullstellensatz. Okay, some are equivalent, some are a little more equivalent than other. So okay, let me say the following, that the affine variety attached to a reduced, I forgot to say this word, you should have caught me, affine K algebras, K algebra is its maximal spectrum. So if you do make this choice, if you take a polynomial ring and then map it onto, and then look at all the take an ideal which is so give me an algebra A, affine algebra reduced, and then I write this as k x1 x2 xn, and this is an onto map, and then I take the kernel, and therefore I know this is an isomorphism, and then this will be a radical ideal because this is a reduced algebra, and then I look at points here which satisfy all the equations, right? Okay. Now those are precisely, you can think of them as being in one-to-one correspondence with maximal ideals of this ring. Okay. So every maximal ideal is obtained by getting taking a map from there to so I say so with this notation, maximal ideals of k x1 x2 xn by I, which is equal to A, are in one-to-one correspondence with points Vi sitting inside A and K. Okay. Now, so you look at the maximal spectrum. So it is the abstract way to do this connection is by doing the maximal spectrum. So you take the maximal spectrum, and then what is the topology you give it? Well, on the spectrum there is the Zariski topology, where V of I, the closed sets are of the form those containing I. So you just take the subspace topology. Okay. Now and that's how you make this, for example, the more abstract, that's how you define the affine variety. And the fact that given 2 points, now why I got into this was because of this, given 2 points, I want a function which is 0 here and non-zero here, or 1 here. So that is the same thing as to say that it vanishes on this means that it belongs to that corresponding maximal ideal. Okay. So given 2 maximal ideals M1 and M2, I want something that is non-vanishing on this, meaning it is not belonging to this but belongs to this. Okay. So how do I do that? Well, I know that this is equal to, these are maximal ideals distinct, therefore this is equal to kx. Right. So I can write this 1 is equal to some f plus g. Okay. Now let us look at now on this point M2, g vanishes. So f equals 1 and f vanishes on this point because it belongs to M1. Okay. Is that okay? Let me write f1 f2. This is here, this is here. If you do that, that is, so the point is this f1 is the one you want. It vanishes on the first, it belongs to the maximal ideal, therefore it vanishes on this. On the second one, this one vanishes. So if I evaluate this, if I think of this equation as an equation of functions and evaluate it on the second point, that's like saying this one vanishes. So f1 evaluated at that point is actually 1 evaluated at that point, therefore equals 1. Okay. So is this clear? So that you can think there is that underlying thing going on there, which you should review. Okay. And if you have difficulty or if there is something that you don't understand, by all means ask. Okay. So I may or I will restrict myself to making some random comments of this nature as the course goes on. Okay. So it is up to you to review it and go back and read chapter 1 again and again until you are fully comfortable with it, and if there are any questions, of course you can ask. Okay. So is this clear? But so this implies fine. So there is no way this can happen unless G inverse equals 1. Therefore, G equals 1. So from here we have G inverse equals 1 implies G equals 1, and that proves the faithfulness. All right. Okay, maybe let's just take a minute. Maybe let me ask you. So how many maybe so there are many versions of the Nullstellensatz charts. Can we recall some of them? In its most basic form, it is just a generalization of the fundamental theorem of algebra. Right? What does the fundamental theorem of algebra say? That if you take, say, over the complex numbers, if I take a non-constant polynomial, that has a 0. Now, if I take a non-constant polynomial in several variables, that has a 0. In so in its most basic form, it's saying like that. But so you want to tell me some? I'm waiting for just to know how much you've seen of this. So for example, there is one version which says, suppose I take an ideal, take its variety, and then take its ideal. Then what do I get? I get the radical. Very good. So this says, for example, so this is k equal to k bar always, right? And I is in k x1, x2, xn, say polynomial ring, and then v of I will be contained in a and k, right? So if I take I take v of I and then take I of v. So I use this notation. You can just for this means all the elements of this which vanish on all points here, right? This is equal to radical of I. Okay. So which way is true in general? Meaning, if I don't assume k equal to k bar, which way is it? This is always contained in here. So this is true even if k not equal to k bar. Okay, there is a there is something called a ring theoretic version. Have you by any chance looked at this? Some of you have done. Okay, so here it's stated as follows. So have you? So there are two terms used in the literature. Sometimes it's called Hilbertian, sometimes it's called Jacobson. In Atiyah MacDonald, I think it's called a Jacobson ring. You know what a Jacobson ring is? Chapter 5 exercises, if you have done that. Okay, let me remind you. Jacobson ring is one which has sort of sufficiently many maximal ideals. That is, every prime ideal, or equivalently every radical ideal, is an intersection of maximal ideals. Okay. So, that is called a Jacobson ring. Okay. So, a ring theoretic version of the Nullstellensatz says R is Jacobson implies Rx is Jacobson. And there are various slight versions of this statement which are less powerful or more powerful depending on the context. Okay. Now, I mentioned this Jacobson thing because it is it might help you. So, remember, you have to prove 1.9.5, right, that the image of a morphism of varieties contains an open subset of its closure, right. Okay. That proof is a little involved, and so it is there if you look in. Of course, it's there in this book, but if you want to go back and look in atomic knowledge, it is there. So it's mostly in chapter 3, but maybe some part there are other. This is in chapter 5, and this will be useful. If you do, there are many exercises here on this Jacobson ring. Okay, it's a good set of exercises to try and do. Some of which may not be relevant to us directly, but in any case, it will clear up your basic algebraic geometry, correspondence between reduced algebras and affine varieties. You'll clarify. Okay. So let's see. Okay, let's go to Jordan decomposition. So let me put down the theorem. G is a linear algebraic group. Now we can say that with impunity, right? Meaning since we have now proved that affine algebraic groups are linear algebraic groups, we can use the word with even more confidence. Okay. Given G in G, there exists unique elements GS and GU in G such that G is equal to GS GU equal to GU GS, and okay, so he writes rho G. Okay, what does this rho G mean? Okay, now he is thinking of a rho for R for right. Right, so there is a right action on Kg. So rho G of f of x is f of xg. Okay, this is the definition of the right action. Okay. Now, so rho G is a linear transformation on this vector space. Okay. Now, this is infinite dimensional. Nevertheless, it is a union of finite dimensional G invariant spaces. I mean, we have noticed that for the left action, the same is true for the right action. Here we are using the right action. Okay. Now, so for rho G, although this is infinite dimensional, it is a union of finite dimensional, and your finite dimensional Jordan decomposition is, there is so much structure in it that in this case you can also define what it means. So, it makes sense to say, if I give you a linear transformation on a infinite dimensional space, but which is locally finite, you can also talk about its semi-simple part and its nilpotent part or unipotent part, as the case may be, if it is invertible. Okay. How do you do that? Well, it as a linear transformation, right? I have to say, give this as a linear transformation. So, how do I do this? Choose an element of this vector space. Now, choose, it is after all locally finite. So, choose a finite dimensional space in which it is contained. Okay. And then I say that the semi-simple part acting on this element is the same thing as the semi-simple part of my action on this part, and you take, you define it that way. Now, the problem is that, so that is the way I define on any given element. Now, you have to prove that it is independent of the choice of G stable vector space that you made containing this V. Well, if you made a V and I made a W, we are all sitting inside V plus, we are both sitting inside V plus W, and the way it works is it's consistent. So, this it has to match. Okay. So, so what you do is the following. So this makes so this is not a capital N. So, is this so the way he is going to define the semi-simple part and unipotent part is the following, it's how it's going to do it. First, you look at rho G. Again, see, how do you do it in Lie algebras? Well, you take the adjoint representation and you define it, and then you prove that it doesn't matter, right, wherever you go. So, here the God given representation is Kg itself. You can choose right or left, doesn't matter, here is choosing right. Okay. So, you choose the right, and then I want to say that the semi-simple part is just look at it as a linear transformation on that, take its semi-simple part, which is rho G S. But then I have to say that it is, but I want an element not as a linear transformation on Kg, I want a group element of the group, right. So, the claim is that there do exist GS and GU such that this thing is actually rho of, there is an element GS in the group which actually is rho G sub S, whose rho is rho G sub S, and there is an element GU in the group whose rho is rho G sub U. Okay. Is the statement clear? And they have these properties. So, now this is how you define the semi-simple and unipotent part of, of course, that is not said here, but once you do this, it's clear. So, you say GS is this is now an element of G, you call that the semi-simple part of G, and GU the unipotent part of G. Okay. Now, second, so this is the existence of Jordan decomposition, if you wish. Second, if phi from G to G prime is a homomorphism of algebraic groups. Then phi of G S is phi of G S, and phi of G U is phi of G U. So this is the analog of the preservation of Jordan decomposition, which you might be familiar from Lie algebras. So, it's consistent with homomorphisms of algebraic groups. So, if I split it here and push it, or push and split, doesn't matter. I get this, it's the same. Third, there is also, finally, you have to say that, okay, all this is fine, but if G prime were GLN, then for GLN I have two definitions now. One, as an algebraic group, I have this GS which has these properties, which is defined like this, but then I can think of it as a matrix and define, and we have to say that those two things coincide. Okay, so that's the third part. So if G equals GLN, then GS and GU are the semisimple and unipotent parts are the usual. Okay, now again I feel that there is not much point in trying to give the proof in gory detail. Okay, I hope the statements are clear. Now I'll go through the first part of the proof, because there is some abstraction there, and it might be good to go through how he is setting it up. Okay, but the details are fairly straightforward, and I will feel free to skip them. Okay. Once again, you should remember that these are not the original sort of proofs that you would think of maybe at first sight. Okay, so these are being worked on, and people have seen and how to make this more efficient, even the definition perhaps of, but more intuitively it is like I would think like this. I mean, you know G is sitting inside some GLN, and the point is that in GLN you decompose, and then the something to prove is that the semisimple and nilpotent parts are still, if G satisfied some polynomial equations, then GS and GU would also satisfy those polynomial equations. If it is a closed subgroup of GLN, then GS and GU would also satisfy those. Okay, that's an interesting thing to prove. Try and think of independently. Okay, and the second thing is that so that would give you one definition, and then you would have to somehow do some kind of stand on your head or something and prove that if you had two different embeddings, then and you get two different decompositions, then in fact they are not two but the same. Okay, that's intuitively how I would still think of it. Okay. Okay. Okay, so let's see how he sets this up. Okay, so this is the first part of the proof. So sketch of the beginning, so that I am absolved of all responsibility. Okay. So let's write M kg tensor kg to kg. This is the algebra. It's an algebra, so there is a map like this. Okay. Now rho g, he says, so this call this M. This is the multiplication. Okay. Now remember, this has nothing to do with the multiplication in the group. This is just the multiplication. This is a commutative multiplication, which just is multiplication as point-wise multiplication of functions. That's all it is. It exists even, yeah, it exists even for a variety. G need not be a group for this to exist. Okay, since, okay, he writes, let's see if you agree with this. Now this is because rho is an algebra automorphism. Sorry, rho g is an algebra automorphism. So this is an algebra multiplication, and you have an algebra homomorphism. What does it mean for something to be an algebra homomorphism? It's a map from the algebra. Here it is the same algebra, but if I had some A tensor A to A is an algebra, and if I have a, what does it mean for some map from A to B where B is another algebra to be an algebra homomorphism? Well, I have a map from A to B such that if I take, you can write it as a commutative diagram. A tensor A to A you have on top, B tensor B to B, let's say, is on the bottom, and you have the vertical map on the right, A to B, and on the left I can put the map tensor itself. So A comma A tensor A prime going to, if you call the map phi A tensor phi A prime, that map, and this commutes, right? That's the statement that that's exactly what it means to say that phi is an algebra morphism, right? That's exactly what that is. If you do rho g tensor rho g and then M, it's the same as doing M and then rho g. Okay. Okay. So it follows that M of rho g. Okay. So what he has done is, so here, so he is pushing it all under the carpet, so to speak, about Jordan decompositions for vector spaces, possibly of infinite dimensional but locally finite. Okay. So the statements he is making is, suppose V tensor W, right. So if you have a, so let's take the following. Suppose I have G is a linear automorphism of V, W, H is a linear automorphism of W, then G tensor H is a linear automorphism of V tensor W. And if I want to take the semi-simple part of that, what do I get? I can just look at GS tensor HS. For the unipotent part, I can take GU tensor HU, okay, and so on. Okay, so he has proved all that. Okay, so, or I at least asserted all that. Okay, so he is going to say is equal to rho g s of M. Okay. This means that rho g s is also an automorphism of A. applies because, and that is precisely the statement that the diagram commutes. Correct? And therefore, it is an automorphism. So, what is an algebra automorphism? It is a linear map from A to B in general, but here it is A and B are the same, which makes this diagram commute. Right? So, rho GS is a linear map, and since so what he has proved is what is involved from here to here is two things, that if I have a V to W is a linear map of space, and you have okay, so he'll do something like this. Suppose V to W is a right, and this is phi, right, and then you have G. Okay, G of phi is phi of so let me see what he does. H, does he use the same thing or different thing? B, okay. So H. So let's write this because this is on this side. So let me write G here, H of phi. So H is acting on here, G is acting on here. This is linear. Okay. In this case, he is claiming phi of GS is equal to HS of phi. And similarly, for phi of Gn is equal to Hn of phi. Okay, so here is a statement which you might want to just think of. Here is a linear algebra statement. G is since I am writing n, I am just thinking of it as a linear map, linear transformation of V. H is a linear transformation of W. Phi is a map such that it has this property. Then this is true. This is the claim. Okay. Now, if we believe that, then M. So this is a linear transformation on this. This is a linear transformation on this. Okay, and M is a linear map. So applying that, I can slip in the S on the total tensor. Now, and then the second part is that S on the total tensor, if it is a product of two things, it is that S goes through the tensor and you will get this S tensor that S. Okay, so that's what we are using. Clear? Now, and so is this clear now? Why this is an algebra automorphism? Not yet? Okay. So let's yes. What is an algebra automorphism?
Algebra homomorphism, right? So why is it automorphism?
Why is it an automorphism? Okay. So if you okay, that will follow from maybe saying rho G inverse. You can prove that rho G inverse S will be the opposite, the inverse of that. Okay. Let's see. Rho GS is an. Okay. Now, see, let's think like this. rho g okay, it's an algebra homomorphism, all right, correct? Okay. Now G is a rho G is a invertible map. So the semi-simple part of an invertible map is invertible. Right? The semi-simple part of an invertible map is invertible, and therefore that is invertible. There, it's a homomorphism that is invertible, therefore an automorphism. Okay, that's simpler perhaps. All right, does that satisfy you? So we don't have to use inverse. So okay, I repeat. So is this, so the part that it is a homomorphism is clear by the commuting algebra homomorphism. That's just the equality. This equality itself is the fact that it is a homomorphism, and so a homomorphism that has an inverse that is bijective will be an automorphism. That will be all right. Okay, if it has a bijection, you can prove. Okay, so and why is it a bijection? Because it's the semi-simple part of a bijection. Yeah, that is defined for a finite dimensional space. It's just defined as it is. So
matrices and
you can do, yes, for a finite you could. You could.
The theorem as such is there exists elements GS and G will satisfy this.
But we have not. We are going towards that. We are going towards that. The point is, so he's going to do something with this rho GS. See, he has proved that it is an automorphism. He wants to first show that it's an automorphism. So rho, and then somehow show that there is therefore a GS which will match whose rho is equal to. Is that
for him rho GS is all the semi-simple part. So rho G is an automorphism. So what is this rho GS for?
Rho GS is the semi-simple part of that linear map. It's a linear map on an infinite dimensional space from what we have said. That, okay, so when we write this here, what does this mean? Rho G is a algebra automorphism, but never mind. It's a linear map on Kg, and therefore it has a semi-simple part. Okay, because the action is locally finite, you can consistently define a semi-simple part, and we are taking that semi-simple part. And what we have observed right now by doing all this, so far we have actually, the only thing that we have done is to observe that the semi-simple part of an algebra automorphism must itself be an algebra automorphism. Okay, that's all we have done. Okay. Thus, this means that, okay, so I take f going to, he wants to do this. So see, I want from somehow given rho GS, I want to get GS, right? How do I get GS? Okay, what is GS? I must get it's an element of G, which means it's an algebra homomorphism from A to K. So I have to somehow convert an algebra homomorphism from Kg to Kg into one from Kg to K. Okay, so right, and the obvious thing to do is the following, and if you, this is intuitively clear what to do. This V is 1. So let's write this. See, after all, this should be, see, if there is a GS, it should be f of GS, right? Okay, so the justification for this is, right, it's back, you know what to expect, so you write it. Okay, so now this is claim is, what is this? This is equal to, so this is actually what we are doing is kg to kg, this is rho GS, it's an algebra automorphism or a homomorphism, and then this is evaluation at 1. It's the composition of these, right? Now, therefore, it is given by an element. Okay, so thus there exists GS such that f of GS is equal to rho GS f of 1. Sorry. Sorry, I should be careful. Okay, but this is nothing but, so this is so okay, let's prove this. Okay, this implies, so let's because you have given an algebra map from kg to k. So to give, that means you are giving a map, k is an algebraically closed field. That is precisely saying if you have a giving a point on the variety corresponding to kg is the same thing as giving a k algebra morphism from its ring to k. See, the kernel of this map, this is an algebra homomorphism, so it's onto, the kernel is a maximal ideal. Kernel is a maximal ideal, and that is so that defines for you this element G, some element, and that you call GS. Yeah. Okay, so that is a point of C. Okay. So now let's see why this is. So you got your hand on what you wanted, right? And then you have to now show this, right? For this, he does the following. So okay, since rho g commutes with all left translations lambda of x, which are locally finite, he says. Or rather, these are locally finite. Okay, so let's write out some. So he's writing. So if some linear transformation commutes with some other linear transformation, if a linear transformation A commutes with a linear transformation B, then the semi-simple and nilpotent parts of A also commute with B. Okay. So let's see rho. So let's rho G S F X is equal to, okay, this is, he writes, so this is, you can lambda x or lambda x inverse of rho gs of f acting on 1, because by definition this acts by this acting on this function evaluated some point is just putting this here, I'll get precisely this. Okay. Okay. Now that is equal to this, these two commute. So you can think of this acting first and this acting second, but I can commute. Therefore, I can act rho gs of lambda x inverse f acting on x, acting on 1. Okay, that's equal to, okay, now what does this do? This is lambda x inverse f acting on 1 times gs. Sorry, so this I have to write S. Okay, so we have this now. So let's see if something, look at that. This equality comes from here. Rho of G sub S on something evaluated at 1 is equal to f of gs. So rho of gs of something evaluated at 1 is equal to that something at gs. Now, but then this again is f of xgs, right? Now this is equal to rho g now inside S f of x. Okay. Now see this. Okay. If you look at that, stare at that, what do you get? You get that x is general, so you can cut the x. Then f is general, so you can cut the f. So you get rho gs is equal to rho gs. Yeah. So there's a little more. I thought I'd get a little farther ahead today, but that's always the situation. You always think you will cover more than you actually can. Okay, but yeah, I'm sure you're, do read the book. Okay, so I understand you might have many courses, other courses, and time. Do read the book and do the exercises, and I'll be happy to, I'll be really happy to have you ask questions. Okay, as you can see here, there is, it's all routine stuff, but at one level, but maybe not yet routine for you. Okay, so I mean, the point is to have it become routine. Yeah. So, see you on Wednesday next week.